So you have to start considering these models. Note that the CD player is a multiple input, multiple output, but we just take a channel. You just take a channel, the first channel between the first input and the first output, and take this transfer function, this system, and you have to check if how the eigenvalues are, and then you have to plot the step response, okay, and then you have to characterize the step response in terms of the moments of a transfer function, okay. Those are values of the transfer function and its derivatives at specific points. For instance, at 0, okay, and this is related to the step response and so on and so forth, okay. All right, I'll just have a short mention about the moments when we go back to the lecture slides, okay. So then I ask you, what is the relation between the 0 moment and the steady state step response? And you'll have to see the connection, that they are pretty much, they are uniquely assigned to each other. So the moment is necessary and sufficient to determine the step response, for instance, the moment at 0, okay? And then I'm asking you to consider a simple system, a 0 system, okay? So that's an amplification, that's a constant system, K positive, okay? To make it a system, okay, to use this number as a system, you have to use this MATLAB command, transfer function, using K and 1, okay? 1 means that the denominator has no S in it, okay? Then you have to plot the step response of the K0 versus the CD player, okay? And I'm asking you for which value of K you can recover an identical step response, okay? It's quite important. And then I'm asking you to consider the same issue. I'm asking you to consider the same issue for a first order transfer function, okay? And then I'm asking you to plot the Bode plots, and then I'm asking you to analyze it. So essentially what I'm asking you is to try to approximate your CD player or your system with a 0 order and a first order system. And I'm asking you to use as an approximation criterion, okay, the relation between the steady state responses of the original system and the approximation, okay? And the relation to the notion of moment, because this is going to be a part, one of the methods, one of the techniques to perform model order reduction, okay? So I'm asking you to play with it to get a flavor of how model order reduction is done. I see there is a mistake here. I don't understand why. Trying to get out of this Moodle somehow. Not catching why it. Okay, I don't want to be open in the browser anyway. Okay. Right. Oh, so this is the Teams. I'm going back to the Teams. It's not working. I want to get out of this Moodle. It seems to be the problem. Maybe if I log out. No. Oh, yeah, there it is. There it is. Okay. Okay, so is this clear? Is the assignment clear or not? I'm asking you.
Yeah, it's clear.
Okay, fine. So you have a week to complete this task, okay? You can start filling out the Moodle at 6 o'clock, and it's open until next Thursday at I think 11 p.m. or so. Okay, just take a look and then try to do the assignment. If you have any problems, if you encounter any issues, any hindrances, please feel free to contact me and we can discuss about it. All right. Okay. All right, mates. Let's carry on. So last time we were discussing, what we did so far in this chapter was this. We have ABCD. This describes a dynamical system. Okay, so we looked at stability. Transfer function. Okay. TS is CSI minus A inverse B plus D. Okay. We looked at responses of the transfer function and the system. Okay, the response is computed using only the ABCD matrices. Okay, and then we had structural properties, then realization, and this is where we stopped. We have to solve this realization problem. Okay, the realization problem. The realization problem is this: given TS, okay, find A, B, C, D such that TS is CSI minus A inverse B plus D. And we saw how we can do that. We saw how we can do it. Okay. First of all, ABCD is not unique, unfortunately. Okay. This is not unique. Okay. And then we had the canonical. Okay. The canonical controller form and the canonical observer form. I'm using the Romanian acronyms. Realizare standard controlabilă, realizare standard observabil. Okay, the controller and the observable. Okay, and from all these, extract minimal realization. This is what we have to do. How to extract minimal realization. This is not an approximation problem, okay? So this is an exact problem, okay? Not approximation, okay? Model reduction that we are going to pursue afterwards, that's an approximation. That's an approximation, okay? But this is an exact problem. In order to do that, first of all, the first question that springs to mind is who or how much is the minimal dimension we can compute? Okay, how much dimension do we where can we stop when we compute the minimal realization of a specific transfer function? Okay, or the minimal realization extracted from a potential ABCD we have just recovered using the standard canonical forms. To do that, we need to introduce the notion of Markov coefficients. Okay, so they establish the relations between two realization of a proper rational matrix. Okay, first of all, of course, you need to have the two D matrices equal. That makes sense. Okay, so now you take the strictly proper part. Okay, so T tilde S, I remind you, it's TS minus D. Okay, and this is strictly proper. Okay, so that means that TIJS are functions BIS over BIJS over AIJS, okay, with degree of A strictly larger than the degree of B. That's strictly proper. Okay, it's a strictly proper transfer matrix. Okay, so we develop T tilde S in a Laurent series. This is something from complex analysis. Okay, a Laurent series is an extension of what we know from real calculus, um, from real function analysis. Okay, the Laurent series is an extension to the other side. Okay, to the minus part, if you like. Okay, so we take a Laurent series of t around s equal to infinity. Okay, and we get for any s with a norm strictly larger than a specific radius, where r is sufficiently large, so where you don't have, so usually when you take this this Laurent series, you have to take it in an area where there is no discontinuities. So essentially, you pick the space where the function is analytic. Okay. Okay. So t tilde s is an analytic function. Analytic. Okay. So that means it's equivalent to saying it's continuous and continuously differentiable. Okay. So when you do the series development, you have to do it in an area where there is no discontinuities. So that means you have to do in a so-called region of convergence of the transfer function. Okay, and that's usually outside such a region. For instance, if you have Ts is 1 over s plus 1, okay, that means that t of minus 1 goes to infinity. Okay, right? Since s equal to minus 1 is a pole, okay, is a pole of this complex function. Okay, yeah, complex functions have zeros and poles. Poles are the discontinuities. Okay, so I recall for any Ts complex function, t of p equal to infinity plus minus infinity equals pole, and t of z equal to 0 is a 0. Okay, right? So t equals minus 1 is a pole. Okay, so you cannot do a Laurent series in this part where the pole exists. You cannot do it here. Okay, because you have this discontinuity. So essentially, you draw a line here, and you say, I'm doing the Laurent series to the right-hand side of this part, and you can draw a line here, and you can say, I'm doing a Laurent series expansion to this side. Do I make myself clear? I think you understand. So essentially, this exists, okay, where there is no discontinuity. Okay? All right? So now, since we're all clear and legal mathematically, we can say the t tilde s admits a Laurent series expansion. Actually, this is not developing. This is a bad word. Expanding should be the word. Expanding. Okay? This is an expansion. This is not developing. Develop is something else. Okay? So expanding in the Laurent series, you get this. Okay. Now you can make an identification of the coefficients in this. So we have to use the relation number 2. This is the relation number 2, okay, where Ts is a fraction of two polynomials. The denominator polynomial, which is a polynomial with matrix coefficients, constant matrix coefficients, and the denominator, which is a regular constant number coefficient polynomial. So 6 equal to 2, 6 equal to 2, yeah, 6 equal to implies that k index k minus 1 is gamma 1. Look, this is around infinity. That's why you have s to the power minus 1, s to the power minus 2. K times k index k minus 2 is gamma 2 plus gamma k minus 1, gamma 1. Okay, these are the coefficients of the denominator, I remind you, and so on and so forth, down to 0, down to this one. So this one can be solved recursively. Can you see that? You first determine gamma 1, then you determine gamma 2, and so on and so forth, up to gamma k plus I. Okay, where you stop at a certain index I, which is larger than 1. Okay. The matrix coefficients gamma I, which you have just computed through this relation, okay, they are called the Markov coefficients of the rational function Ts. Okay. Hence, if ABCD is a realization of Ts, okay, then this is the formula of Ts which we're familiar with. Then it's equal to this development, okay, to this expansion. This is easily computed, okay? This is easily computed. So you just take it out, and then you use this here, okay? So this is easily computed. D, C, B, C, A, B, C, A squared, B, and so on and so forth, okay? The coefficients, yeah, of course, where S is larger than the spectral radius of the matrix A. The spectral radius is the one giving the largest eigenvalue of the matrix A, because the poles of Ts are uniquely determined by the eigenvalues of the matrix A. So the poles of Ts are essentially among the eigenvalues of the matrix A. Okay, but to be safe, okay, you just take the spectral radius, so you go to the largest eigenvalue, and then you do the expansion beyond this eigenvalue, because you take it at infinity anyway. Okay, so these coefficients from D to Ca to the power I minus 1b for any I larger than 1, they're called the Markov coefficients of the system, or of the realization ABCD. Okay, so essentially identifying the coefficients in 6 and 7, you get this relation. You get this relation about the Markov coefficients. Okay, about the Markov coefficients. What you usually do, essentially, if you want to make it easier, if you have Ts is C S I minus A inverse B plus D, you take the change of variables. You do the change of variables. I'm using an abusive notation. S becomes 1 over S, and then you get T tilde of the new S, or whatever. You can know. Let's make it, no, let's change the name, okay? You take the change of variables S equal to 1 over Z. This is easier. And then you get T tilde Z, okay, which is C, what? Zi minus A, no, I minus AZ, sorry, right? I minus ZA inverse, and there has to be another Z, right? And he comes out like this, ZB, right? Is it correct? I think so. And then you can take the expansion of T tilde Z around Z equal to 0. Yeah, this is equivalent to S goes to infinity. Okay? And then you get all the coefficients. Okay? Plus D. Okay? So the first coefficient, TZ, T tilde 0, okay? This is D. This is gamma 0. Then you have to take the derivative of this, t prime z, and this is what? You have to make the derivative of this, okay? So this is minus CA I minus ZA minus 2 ZB. So this is 0, this doesn't count, plus CA I minus ZA minus 1 B. Okay? So that means that T tilde prime of 0, okay, for the second coefficient, okay, is CAB. This is gamma 1, and so on and so forth. So essentially, I showed you, or CB, something like that. Maybe I did it wrong. Oh, CB, yeah, because Z is equal to 0. Sorry, CB. Okay, because Z is here, so you substitute the 0. Okay, then you take again the derivative and so on and so forth. Okay, and you can easily prove these are the relations indeed. So these are the Markov coefficients. Okay. So therefore, all the realization of Ts have the Markov coefficients which are identical to T of S. So these are invariants. That's how we call them. They are invariants of the system. Okay, so the Markov coefficients of a system are invariants. So does this mean? This means that if you go to A tilde, B tilde, or hat, if you take for Ts the same Ts, instead of A, B, C, D, you take the realization A hat, B hat, C hat, D, okay, and A hat is TA T inverse, and B hat is TB, and C hat is CT inverse for any T, an invertible matrix. Okay, then gamma I tilde, which is C A to the power I minus 1 A tilde B tilde hat, sorry, gamma hat, equals gamma I, which is C A I minus 1 B. This is what it means, and you can easily prove that because you have all the ingredients here. You can prove it yourself. Okay, so this is true. So all the realization of Ts have the same Markov coefficients. Okay, so invariants, Markov coefficients are invariants of Ts. They're invariants, so the realization doesn't count. For any realization, you get the same Markov coefficients. Now, based on the Markov coefficients, we introduce another interesting quantity, which helps us get the minimal dimension. This is called the Hankel matrix. This Hankel matrix actually will come. You'll notice that later. This comes from an infinite dimensional operator, which is the Hankel operator. Okay, which is defined on the input in the past, on the past inputs to the future outputs, okay, and it's an infinite dimensional operator. This operator is depending on this Hankel matrix. But here we use truncations essentially because I said it's infinite. This is not infinite, this is finite. So we introduce the so-called Hankel matrix, which is this finite matrix made of the Markov coefficients. Look at the structure of the Hij matrix in relation 8, please. Have a look at it. Okay, this is how you build the so-called Hankel matrix. But if you look closely, okay, The Hankel matrix, look at the structure, look at the shape, okay? The Hankel matrix is actually the controllability, the observability matrix in I steps times the controllability matrix in I steps, okay? All right? So this is very interesting, okay? This Hankel matrix is the product of controllability and of the observability and the controllability matrices, okay? I think this is J here. Okay. All right? Where Rj is the controllability matrix in J steps and Qi is the observability matrix in I steps. So these are portions of the controllability and observability matrix introduced last time. Okay? So now it follows that for any two realization A, B, C, D, and A tilde, B tilde, C tilde, D of the same TS, that means related through a specific coordinate transformation, we have that Qi Rj is Qi tilde Rj tilde. Okay, so this is another. So this just like the Markov parameters were invariant with respect to coordinate transformation, this holds as well for the Hankel matrix. It's invariant to coordinate transformations. Okay, this is very important. So that means that the minimal dimension must be probably unique, and it's not. It doesn't matter what kind of numbers you've got in the matrices, as long as they have the same dimension. The matrices have the same dimension. Okay, so the dimension is invariant. The minimal dimension, not the matrices. The matrices can be changed through coordinate transformations. Okay, however, the dimensions of the matrices cannot. Okay, right. So although the Hankel matrices have arbitrary large dimensions, note that their rank is bounded by n. Okay, by n. The dimension of the system. Now the question is, okay, bounded by n, but the question is n the minimal dimension? Is n the minimal dimension? Or even better, what are the conditions such that n is minimal? These are the questions we need to answer. Okay. All right. Now I'm going to ask you to excuse me for a second. I got to go to the gents. Let's have a 2-minute break, and I'll get back to you. All right?
Okay. Okay.
Fine. All right, let's carry on. Okay, so like I was saying, let's answer the question: what is a minimal realization, and actually, what is the minimal dimension of a specific transfer function? The minimal dimension of a realization of a transfer function. Okay. Just remember that the dimension of the realization of a transfer function is given by the dimension of the denominator. However, the transfer function, okay, transfer matrix is a bit more difficult, but the transfer function can have identical poles and zeros, which need to be simplified. Okay, so you have to be careful about how you do or who you do call the minimal dimension. So essentially, a realization ABCD of dimension f of the proper rational matrix TS is called minimal if any realization has the state space dimension less than or equal to n. If any of the realization has the state space dimension less than or equal to n. Okay? And a necessary and sufficient condition, and this is the crucial result, necessary and sufficient condition of minimality of a realization is called minimal if and only if it is both controllable and observable. That's the answer. This is the key to everything. Okay, so you write a set of differential equations for a specific transfer function. If you manage to prove the controllability and the observability both, then you end up with a minimal realization. That means that the set of equations that you have written for your transfer function, they are the only necessary and sufficient equations to describe the dynamics of that specific transfer matrix. This is the reason. And here we have a proof of the things. First of all, we show that the condition is necessary. You assume that the realization of dimension n is not controllable and or not observable. Okay. Then by state space equivalence transformation, you bring the system to the structural decomposition, as we have just learned. Yeah, we learned this last time, how to perform a structural decomposition, how to extract the controllable and or observable part from any realization. Hence, the realization, we call it A22, B2, C2, D, okay, from the structural decomposition. Let's see if we have it here, if we recall it. It's a few slides back. Okay. No, it's not here. It's in the previous chapter. Okay. We have this in the previous chapter. Okay, where we discussed structural properties. But I have here. Let's see. I have here. Oh, this it is. Here it is. So close to the end of this chapter, we have here the structural decomposition. This is what I'm talking about. Okay. So you extract the blocks A22, B2, C2. Okay. And they represent, look here, they represent the controllable and the observable part. And this essentially is the realization. And now we're trying to say that this controllable and observable part is actually the minimal realization of TS. We do this through denying, okay, through denial. So we deny that A, B, C, D is controllable, even if it's assumed minimal, okay? Then by the state space, okay, if it's not minimal, then we can apply the structural decomposition from the last chapter, and we get this this realization A22, B2, C2, D with a dimension strictly less than n, okay? But this contradicts the minimality assumption, so this is ridiculous, okay? Because n is the minimum, there is no other less than n, okay? The condition is sufficient, okay, and this goes for observability as well. Okay, so they are the same thing. The condition is also sufficient. Now this is a bit more difficult. So it's sufficient that the system is controllable and observable, so it is minimal. Assume the realization of dimension n is both controllable and observable. Okay, then the rank of the controllability and observability matrices of dimension n in n steps. So they are the matrices, the controllability and observability matrices of the system. Their ranks are n. Okay, hence the rank of Qn times Rn is the rank, for instance, of the matrix Rn. This one. This is a relation from matrix theory, minus the dimension between the intersection of the image of Rn and the kernel of Qn. And this is n. Okay. Again, assume by the contrary that ABCD is not minimal. Okay. Then there exists another realization A tilde, B tilde, C tilde, D of dimension n tilde with n tilde strictly less than n. Okay. So if you deny this is what happens. From relation 10, which is this one, okay, from relation 10, okay, you get this, okay, you get this, all right, but this is not possible. This is not possible since the rank Qn is strictly smaller than n tilde and rank Rn tilde is strictly smaller than n tilde. This cannot happen. This is very easy. Okay. Yeah. And we just mentioned that in general, this must be true. Okay. This is what this guy is saying. This is what this guy is saying. This is usually true. Okay. This is usually true. So the ranks should be the same. The ranks should be the same. And this is not possible. Okay. So the assumption is wrong. So indeed, it's a necessary and sufficient condition. So it's a powerful result, and it's the result we make use of. Okay. Another important result about minimal realization is saying that any two minimal realizations of a proper rational matrix TS are state space equivalent. Okay. So the minimal realization is not unique, and the non-uniqueness is given by the coordinate transformations, the T matrices, okay, T inverse, these kind of things, okay. Hence, let's prove that any two minimal realizations are state space equivalent, okay. Consider A, B, C, D, and A tilde, B tilde, C tilde, D, two minimal realizations of the same transfer matrix TS. Okay, according to the previous result, both realizations have the same dimension and they're both controllable and observable. Okay, from relation 9, however, this is relation 9. Okay, it can be easily seen. Okay, can be easily seen that Qn Rn plus 1 is also Q tilde n R tilde n plus 1. Okay, or QNB BA Rn. Okay, because you just show how Rn plus 1 is BA Rn. Okay, is equal to this, from which you have that QNB equals this guy. Okay, this guy is the same with this guy. Okay, and this guy is the same with this guy. Okay, now since we have these other properties, that Q is injective, and the matrix, and I think here is an n missing, and the matrix Qn tilde Qn tilde transposed Qn tilde is not singular, and using the first relation in 13, which is this one, okay, we have that B tilde is TB with a where we can pick T to be this matrix. We can pick T to be this matrix. Okay, and we get similarly, Rn is a surjective matrix, and Rn transpose tilde Rn Rn tilde transpose is a non-singular matrix. And from the second relation in 13, so using this guy, using this relation here, it immediately follows that A tilde is TAS, where S is this matrix. Okay. All right. And here we should just do it like this. Okay. These are missing the brackets. Okay. So from relation 12, we can write this relation here. And then we follow this guy. Okay. So the two realizations, they are state space equivalent, provided we further show that S is T inverse. Okay, so we managed to get a coordinate transformation and explain how this coordinate transformation works, but you get one based on the first relation in 13, and the other one, you get it based on the second relation of 13. Now, the trick resides in proving that both coordinate transformations are actually identical. And indeed, you can see here that TS is the equals the identity, and it also equals ST. Okay, it also equals ST because you have these relations here, and you just do all the tricks, and you know who these guys are. Okay, and then these things are, look, so here you see an identity, and here you get the other identity. Okay. I'm not exactly sure why this is written twice here. I think it was supposed to be the other way around. True. We should also have ST. Okay. So indeed, they are one and the same. So we've just proven that any two minimal realization of a proper rational matrix TS are state space equivalent. Okay. So minimality, or the minimal index, or the minimal dimension, is invariant to coordinate transformations, which was to be expected. Okay. All right. Now, we consider mu and ni the smallest integers for which the rank of the Hankel matrix up to mu and ni is the Hankel matrix up to nu plus I, ni plus j. Then, if this is the smallest integer for which this relation is correct, then mu equal to ni is the dimension of the minimal realization. So the dimension of the minimal realization the dimension of the minimal realization is given by the rank of the Hij Hankel matrix. Okay, so you compute up to order n, and then you compute to order n plus 1, and if the ranks are the same, then the ranks are n in both cases, then the minimal the dimension is n. Okay, all right. So you compute up to a specific order. Okay, mu and ni, okay? And if you check if this relation holds, then indeed you come across, or you discover, or you unravel the minimal dimension of the system. Is this clear to you? How we determine the minimal dimension of a system? You have to look at the Hankel matrix. The Hankel matrix is the key to determine the minimal realization for any ABCD system. If you have any questions, please, if it's clear or not to you.
It's clear.
Okay, so this is where you have to look. This is where you have to look. All right. Good. We have a remark here. For any proper rational matrix TS, we can compute the unique Markov coefficients using the decomposition 6. Let's see what 6 is. This one. Okay. So just compute this one. All right. Because they are the coefficients of the Laurent series expansion. Okay. Okay. Furthermore, the Markov coefficients says here determine uniquely the double index Hankel matrix sequence Hij that have finite rank equal to n for ij, where n is the dimension of a minimal realization. Okay, where n is the dimension of a minimal realization. All right. Okay. Okay, so we have Markov coefficients, Hankel matrices. Okay, so these are the keys to determine a minimal realization. Okay, so essentially you get ABCD, you compute the controllability and the observability matrix. Okay, you stop up to a certain order n. Okay, and you can go downwards or upwards until you stop and you see that the ranks do not change. You see that the ranks do not change. Okay. Of course, you can compute the dimension of the minimal, you can understand, or you can recover the dimension of the minimal realization thinking about the observable and controllable space, and you can get an idea. But the clear minimal dimension comes from the inspection of the rank of the Hankel matrices. The Hankel matrices are the key to determine the minimal realization. Now, we also have an inverse problem, which is quite fundamental, assuming that you have a sequence of Markov coefficients. So this is data-based, data-driven, how people call it today. Now you get data. You assume you have a sequence of Markov coefficients computed from something or from one thing or another, gamma I, okay? The question is there always a dynamical system to match these Markov coefficients exactly? So we don't talk approximation at the moment. We talk about an exact system that matches, that has those Markov coefficients. It further says here, more precisely, the series in the right-hand side of 6 is always converging to a proper rational matrix, which is the transfer matrix of a specific ABCD system. This is the question. So the question is it possible from a sequence of data to construct a dynamical system to match exactly that data? Well, I'm afraid the answer is no. I'm afraid the answer is no. It's not necessarily possible, okay, to get a dynamical system to measure to describe that specific data. And the next result, we have a result here that gives a complete answer. And this result is the procedure to compute a minimal realization of a proper rational matrix. Assume that you have a proper rational matrix, okay, which is made of transfer functions, which are made of the quotients of polynomials. And assume that the degree of the nominators are always greater than or equal to the degree of the denominators. Okay? The first step is to compute the matrix D. The matrix D is T evaluated at infinity. And then you compute the strictly proper rational matrix T tilde S, which is TS minus D. And this is in the form that we are already familiar with, a polynomial with constant matrix coefficients at the denominator and the normal real number polynomial, real coefficient polynomial on the denominator, okay? Where gamma S is the least common multiple monic, which is monic, of the denominators of all elements of T tilde, okay? And the coefficients Ki are going up to K minus 1, and they are P times M constant coefficients, okay? So they are matrix coefficients, okay? So you do this, okay? Then what you do is you write a canonical controllable realization, or an observable controllable realization, whatever suits you best, okay? Because you have to be smart, you have to take the lower index, always, okay? If you have, okay, controllable realization, and I would say here, remark, or observable realization, okay, if P is smaller than M. And here, canonical controllable realization if M is smaller than P. Because look, the M and the P come into M, and you don't want to start computing your minimal realization from a larger system, but from a smaller system. No, it's only natural to do that. So you pick the canonical controllable or observable form depending on the number of inputs and the outputs your MIMO dynamical system has. Okay? Now, if you use a controller canonical form, of course, automatically the pair AB is controllable. Hence, on this, how do you compute your minimal realization? The minimal realization, we remember from the previous theorem, must be both controllable and observable. ABCD is already controllable. However, we do not know whether it is observable or not. We check whether this ABCD is observable or not. Okay? If it's observable, then we stop. There is nothing more we can do. We struck oil. N is the sought minimal dimension. Okay? Fine. However, if the controller canonical form ABC is not observable, of course, the only thing we can do is apply an observable decomposition. So at step 2, apply the observable decomposition to the pair CA. We know how to do that. We have to find the coordinate transformation such that we emphasize this block structure, such that the pair C2 A2 is observable, of course, and we also use B2, okay? Such that the pair C2 A2 is observable. Step 3, since AB is controllable, it follows that the pairs A hat B hat and A2 B2 are also controllable. So any portion of a controllable realization is once again controllable. That only makes sense, okay? Because if you have up to rank n, if B, AB, A to the power n minus 1B, this is R, okay? This has rank rank. If rank R is n, okay, because this is a remember this is a wide matrix, okay, all right. Any other portion, okay, so if you have here b tilde, a tilde, b tilde, a tilde to the power k minus 1, b tilde, okay, where this is of dimension k minus 1 lines, okay, then rank R is k minus is k, sorry, rank minus is k, okay, because k is smaller than n. This is not k minus 1, but this is k, okay, so you have here k lines, okay, so any portion of this R, the rank holds, okay, the rank condition holds. So any part of the system which is controllable is again controllable. Therefore, the system A22B2C2D, which is input-output equivalent with the original ABCD, we know that, is both controllable and observable, and therefore minimal. Okay? Furthermore, A22B2C2D is a minimal realization, and the transfer matrix is given actually by this part. In the seesaw case, single input, single output, that means that the controllable and observable part is the part that gives the irreducible function Ts. Okay, the irreducible function Ts. Of course, we have to make some comments with respect to the numerical issues of such techniques. First of all, from a numerical point of view, it says here, the algorithm to compute a minimal realization follows precisely the steps of this algorithm. However, the T transformation here is usually an orthogonal transformation because they are much better to use, even orthonormal transformation. We know that in numerics or whatever is orthogonal is very good because it's easier to compute the inverse and to determine the matrix T. Oh, furthermore, just like I mentioned here, depending on the inspection of the number of inputs and outputs, you can start with the dual version of this algorithm. So here you compute the canonical observable realization, and here you apply a controllable decomposition. So this is the dual version of this algorithm, okay, of this algorithm, okay? All right. If you have any questions up to here. If you have any questions until now. Any questions? I'm listening. All right, I'm afraid not. Let's carry on. Now we have to recall, because we are talking about, we remember that we have to compute Gramians, okay? So Gramians, stability, okay? And other things Okay, they are related to Lyapunov matrix equations. Also, we remember from the steady state computation of a dynamical system. Okay, steady state. Okay, plus moments and other issues in control. Okay, they depend on solving Sylvester matrix equations. Okay, so it's only fair here to address and recall what happens to the linear matrix equations. You can also look them up in matrix books, such as the Horn and Johnson matrix book, I think, and also in the Antulas book, which is uploaded on your Moodle. Please consult the Antulas book if you have any inconsistencies or any details you need to clarify about linear matrix equations. They are quite crucial in numerics, and I'm sure that at least the people who followed our bachelor studies here at the automatic control and computer science faculty remember from the numerical methods course that they ran into Lyapunov and Sylvester equation, as well as those who have followed optimization courses. Is it true? Have you seen linear matrix equations before? Or people who followed systems theory courses?
Yeah.
So you saw them. How about the people who have studied economics? Have you ran into linear matrix equations before that you need to solve in MATLAB or something? I'm asking our friend here who's studying economics. Have you come across linear matrix equations before? I'm not sure if he hears us or not. Oh well, even be whatever may be. Okay, fine. I let bygones be bygones. So what's in the past is in the past. We are going to recall here and review an overview a little bit of the linear matrix equations, and you can look into the books I have just recommended for further information. Okay. So it says here that several linear matrix equations, such as the Sylvester and the Stein equations, and their symmetric versions called Lyapunov and the symmetric Stein equations, play a central role in the linear systems theory and model reduction in particular. So you also need them quite often, quite a lot in model order reduction. So these are they are called linear matrix equations because the unknowns, which are matrices, they appear only at power 1. If the matrices appear at power 2, at square, then they become Riccati matrix equations, and they are used pretty much, and you come across Riccati equations in the robust control course that you have to follow now. No, you don't have to follow now. Sorry, that probably some of you followed last year before graduation. Some of you who were at B1. Is any of you who studied B1 before? Hmm?
Yeah, some of us studied that B, but
For instance, B1.
but I studied that A.
Oh, you were A. Okay, fine. So those who are at B1 must have come across Riccati and Sylvester equations also at the robust control course. No matter what, again, since you've got different backgrounds, we're going to recall everything for everyone. Okay, so in this section, we have to present the solvability of such matrices. So the question is, if you have a linear matrix equation, when does this equation have a solution? When does this equation have a unique solution? This is more important, okay? So we have to present or recall some solvability conditions and some remarkable properties of such equations. First of all, just some recollections of some mathematical notions. A matrix is called symmetric if A equals A transposed, and if the matrix has complex numbers, or it's called Hermitian if A is equal A star. So that means its eigenvalues, if A is Hermitian, Hermitian is more than transposed. It also means conjugated. Okay, so transposed or symmetric. Symmetric matrix. Okay. A equals A transposed. Hermitian matrix. A equal A star, and A star is A transposed and conjugated, complex conjugated. Okay, this is called Hermitian. Now, any of these matrices imply or is equivalent, no, it's not equivalent, imply that their spectrum is real. So the spectrum of a symmetric matrix is real. Okay, is real. Okay, so and if A, okay, so Hermitian implies transposed. Okay, this is for real numbers. So if A is a real matrix, then A star is a transposed. Okay, so Hermitian includes transposed, is the higher notion. Okay, so if A is a Hermitian matrix, then all its eigenvalues are real, and we introduce the so-called sign matrix. So the sign of a matrix A is the diagonal of an in minus and in plus, and the rest is zero, where n minus, n plus, and n zero are the number of negative, positive, and zero eigenvalues of the matrix A, respectively. Okay. So this is the matrix of the signs of the eigenvalues. We are talking again about symmetric matrices, so they have real eigenvalues, hence they are real numbers, hence they've got plus or minus signs. Okay, and we are going to make a distinction about it, a distinction between them. Okay, so a matrix having the form in the right-hand side of 19 is called a sign matrix. Okay, this sign matrix is uniquely defined for a Hermitian matrix. Why? Because the eigenvalues are unique. So that means that the Hermitian matrix is never changing with coordinate transformations. Okay, so what it says here, it says that if A has associated sign of A, then back to square one. So if A has a Hermitian, okay, has sign of A, then sign of A hat, which is sign of T inverse AT, is sign of A. Okay, so sign is invariant to coordinate transformations. The Sylvester and the Stein equations. Yes. Consider a matrix A equal F is any set. Okay, can be complex number, real numbers, whatever. So let A be an n by n matrix, B be an m by m square matrix, and C be an n by m matrix. Okay. Then the Sylvester equation AX plus XB plus C equal to 0 has a unique solution if and only if the eigenvalues of the matrices A and B satisfy this relation. Okay. So that means if lambda A intersection with lambda And this is equivalent to saying that lambda A intersection lambda minus B is the empty set. Then it has a unique solution. It's also important to understand when this unique solution has also satisfies a rank condition. Yes, please note that since X, okay, since A is an n-dimensional matrix and B is an m-dimensional matrix, the solution X is an n by m matrix, just like C. So X and C have a similar dimension. So X exists and is unique if this condition happens. For the Stein equation, this is Stein equation. This is it's also called the discrete Sylvester equation. This equation has a unique solution X if and only if, or the generalized Sylvester equation, the eigenvalues of A and B satisfy these conditions. Okay. So this is about the matrix two of the most important matrix equations that we use. Okay. Okay. We also have the symmetric version of these matrices. So the symmetric version is when B is A Hermitian, the Hermitian of A. Okay. So if the condition 21 or 23 does not hold, then the Sylvester equation may have no solution or an infinity of solutions. Okay, depending on the free term C. Okay. So for instance, if C is equal to 0, you might have an infinity of solutions here. Okay, if this condition is not satisfied. If this condition is satisfied, then 0 is the unique solution. Otherwise, this is not true. Okay. So, Lyapunov and the symmetric Stein equation. If B is the Hermitian of A and Q is defined as C, which is also Hermitian. Okay, so if B is the Hermitian of A and C is Hermitian, then the Sylvester equation becomes the Lyapunov equation and takes this form: AX plus XA Hermitian plus Q equal to 0. Whereas the Stein equation is called the Stein symmetric equation, or the discrete time Lyapunov equation, and has this form. Okay, has this form. And now, based on theorem, I don't know what theorem 4 is. Whatever, but we get a new theorem. We get a new theorem here. Okay, where we say when these equations, the Lyapunov and the discrete Lyapunov equation, have a solution. Okay. So consider a matrix A, a square matrix A, and the matrix Q, Hermitian and square. The Lyapunov equation XAX plus XA Hermitian plus Q equals to 0 has a unique solution. If and only if for any two eigenvalues of the matrix A, this relation holds. Okay, so there is no contrary sign identical eigenvalues. Okay, there is no contrary sign eigenvalues. Okay, moreover, if X is unique, then it is also Hermitian. So X in its term, because X is a square solution now, is a square matrix. Yeah, here X was not square. Usually here X is a tall matrix, yeah, or a wide matrix, okay? But in this case, X is a square matrix. So if the solution exists and is unique, the solution itself is Hermitian. The same type of condition holds for the the symmetric Stein equation, or the discrete Lyapunov equation. you realize that this theorem is easy to prove since Lyapunov and discrete Lyapunov, they are only particular instances of the Sylvester and the Stein equation. Okay, so this is all set because these are very important and we're going to use them quite a lot. It says here that we now give a general result relating the inertia of the solution X to the inertia of the matrix A, from which many important theorems on the Lyapunov and symmetric equation follow a simple corollaries. Okay, so we give now some specific results. So given a square matrix A, we denote by these quantities ni Ca, pi Ca, and delta Ca the number of eigenvalues with negative, positive, and zero real parts. Okay, and then we also with D the number of eigenvalues of A with absolute value less than, greater than, or equal to 1, respectively. So this triplet of integers is called the C inertia or the D inertia, the continuous of the discrete inertia of a specific matrix. Clearly, if you add up these quantities, you end up with the dimension n of the matrix A. And the result says that if you have matrices A, Q, and X n squared, and X equals to and X Hermitian and Q Hermitian and Q semi-positive definite, okay, and you assume that they satisfy the Lyapunov equation AX plus XA Hermitian plus Q equal to 0, then we have the following. You have no non-zero eigenvalues. No, sorry, no zero real part eigenvalues. Okay. All right. So no zero eigenvalues. Okay. Also, mu C. So the eigenvalues with positive or with negative sign are more than the eigenvalues with positive sign. Okay. So A has more negative eigenvalues than X has positive eigenvalues, and vice versa. A has positive eigenvalues more than X has negative eigenvalues. Okay, the same holds for the discrete case, but vice versa. Okay, the same holds for the discrete case, but vice versa. Okay, the same holds a similar type of result holds for the symmetric Stein equations. So what is this result showing us? It's showing how many positive and negative eigenvalues your matrix has once you have X satisfying this Lyapunov equation. So if X is the unique solution of a Lyapunov equation, specific sign conditions hold for the eigenvalues of X with respect to the eigenvalues of the matrix A. Furthermore, assume that Q is symmetric and or Hermitian and semi-positive definite, and Q is given in the form BB transposed, okay, where B is any n by m matrix. If the pair AB is controllable, then the inequalities in the previous theorem can be strengthened to equalities, and furthermore, we can draw a conclusion about the rank of the solution X. So consider A, X, B, whatever, and X Hermitian, and assume that the pair AB is controllable. If X is the solution of the controllability Gramian, you realize here X is the controllability Gramian. So if X is the symmetric solution of this Lyapunov equation, then there is no zero eigenvalue in A, so A has no zero eigenvalues. X has no zero eigenvalues. Furthermore, the number of negative eigenvalues is the number of A is the number of positive eigenvalues of X. And similarly, the number of positive eigenvalues of A is the number of negative eigenvalues of X, if I'm correct. Okay? You see, yeah? Okay. And the same, something similar holds for the Stein equation, okay? For the Stein equation. What it says here, so the number of negative eigenvalues is the number of positive eigenvalues of X plus the number of zero eigenvalues of X, okay? And the number of positive eigenvalues of A is the number of positive eigenvalues of X. So what conclusion do we draw here? You remember that we were saying that an A matrix is a stable matrix if the Lyapunov equation has a positive definite solution. You remember that. So in this case, note, if the controllability Gramian is positive definite, that means that this guy is 0, and all the eigenvalues are positive, then all the eigenvalues of A are negative, if A is symmetric, or the eigenvalues of A if A is with negative real part. Okay, so indeed, if X, so from this we have the consequence that we already know, consequence, okay, or the corollary from this we can draw. If delta Cx is 0, which is equivalent to X is positive definite, then mu C A is pi C X, yeah? Okay, so this is saying that A has n eigenvalues with negative real part. This means stable. Okay, so this is just confirming the stability result we know from previous chapters. Okay, it's just confirming that. Okay, it's quite interesting, huh? Same holds for the number of negative X. So since the number of negative, and also this is 0. Okay, and also this is 0. So if nu C is 0, so if delta C and nu C, also nu C X equals 0. So you have to have both conditions. Then it's positive definite, okay? And then you recover the stability result, which I asked you to check in the previous assignment, if you remember, okay? Oh, what happened? Okay, okay. Now, if you replace in theorem 7 or 8, A with A star, 7 and 8, I don't know who 7 and 8 is, probably this is 8 and this is 7, okay? If you replace A with A star and B with C star, we get the corresponding dual versions with the observability Gramian, okay? With the observability Gramian. So it says here that the kernel of X satisfying the Lyapunov equation is related to the controllable space of the pair AB. Okay, so you get the rank of the solution. That means that the rank of the solution X equals the dimension of the controllability subspace. the dimension of the controllability subspace. Okay. Now we can also get a dual result. We can also get a dual result where we consider the matrices. We do the same for the observability. Okay. So we consider ni CA be the unobservable space of the pair CA. We assume that we have the Lyapunov equation in X and C satisfied by the matrix X. So the kernel of X is included in the unobservable space. So that means that if the unobservable space is only the element of 0, then the kernel of X is only the element of 0. So if the pair CA is observable, the kernel of X is 0. So that means that the image of X, so that means that the rank of X is full. Okay. So this means that if then image of X is the whole space, and that means that rank of X equals n. It's full rank. Okay. Now, if the Lyapunov equation has a unique solution, okay, then we can also have this relation, so they become equal. Okay. It's quite interesting, huh? The results that you get here. Okay. Okay. I would say we stop with the theory for the time being. I'm asking you whether you agree or not.
I agree.
Okay, it's a lot of information you need to process. Please read the books. So we have a short break, okay? And then we come back and try to do a little play with the MATLAB. And I'm also happy to answer your questions. So this is a research master. I wonder if you have any questions about all the stuff we have discussed so far, and we can talk about it. Okay. So let's have a break, and then we come back and try to play with a little bit of MATLAB. Okay.
Okay.
All right. Fine. All right, I started sharing my screen. Can you see my MATLAB screen?
Yes.
Okay, fine. That's lovely. I'm looking for some example I used to have. Let me see if I can find it. I have it here. Oh, yeah. Trying to find some example with minimal realizations, okay, which I have used before, so I can show it to you. Okay, so I'm choosing this this matrix. So I'm choosing ABC, okay, of dimension 4, if you can see, okay, and I'm building a state space system. It's a multiple input, multiple output system, as you can see. So I've got two inputs and two outputs. It's a so-called square system, okay, and I'm using um, the command that computes a minimal realization, is minReal, from minimal realization, okay, from minimal realization. So let's just run this and analyze the results. All right, let's analyze it. Okay, let's run. I'm running. Okay, so let's see. Okay, fine. Let's check it. Okay, so we can see this is the A matrix. It's a 4x4 matrix. B matrix is a 4x2 matrix. So we've got 4 differential equations and 2 inputs. And we also compute 2 outputs. And we have no D term, since the D term is 0 in this case, okay? This is a continuous time state space model. Of course, you can build a discrete time state space model in the same way. Maybe it's worth mentioning at this point that there is no difference between discrete time state space and continuous time state space. The notions and the theory is essentially identical, okay? And then we build the controllability matrix. We build the controllability matrix R, and the rank of R is 4, so the system is controllable. However, the rank of Q, if you look here, is 2. So the system is not observable. This is the observability matrix, C, CA, CA squared, CA to the power 3, or CA cubic. Why is that? Because essentially, I must say, look, columns 2 and 4 are identical. Can you see that?
Yeah.
So that means that the rank is less than 3. And probably, and also if you look closely, column 1 is twice column 3. Can you notice that? Column 1 is twice column 3. Agree?
Yeah.
Cool. So that means that the rank is actually less than 2. And probably, if you compute, look at this minor in this corner, 2, 0, 0, 1. This minor is non-zero. Hence, indeed, the rank of the observability matrix is 2. So that means that the unobservable space has dimension 2, and the observable space has dimension 2. 2 plus 2 equals 4. Okay? So that means the question is now how to determine the dimension of the minimal realization. Well, in this simple example, because this is very simple, it's easy. Since the system is controllable, hence the dimension, the minimal dimension of the system is the dimension of the observable space. The observable space has dimension 2. Hence, the minimal dimension of this fourth order system is 2. However, we would like to check this with the Q and R matrices. Okay, so let's compute Hankel. Let's call it H44 because this is of dimension 4. Okay, let's call it Q times R. This is the Hankel matrix. You see the Hankel matrix. This Hankel matrix contains the Markov parameters. Keep that in mind. So these numbers 1, 0, -1, they're all made of the Markov parameters, just like the formula we have discovered, we discovered 2 hours ago. Okay, so these are the Markov parameters. Fine. Okay, hence let's make rank H44. Okay. Oh, what's wrong? Huh? Oh, no equal. Sorry. The rank H44 is 2. You see? The rank H44 is 2. So that means that the minimal dimension of this guy is 2. Okay? Because we just computed this. Okay? We just computed this. Now, if you take, for instance, H33, let's compute H33. And H33 is the matrix Q, which has from 1 to 3 and 1 to 3. Okay? Times the matrix, so it's the observability matrix in 3 steps, times the controllability matrix in 3 steps. So Q R 1, 2, 3, 1, 2, 3, and R 1, 2, 3. This is the Hankel matrix in 3 steps. You see, in 3 steps. So you take only a portion. You take only a portion of the matrices. Okay, you're taking only a portion of the matrices. Okay, and look, let's see if we are correct. If we are not correct, then I made it wrong. Oh, this is actually 1 if you have a look. This is even worse. This is 1. Okay, this is 1. Because I wanted to go actually. So let's see, Q and R. Oh yeah. Let's go to the 4. So that's not H44. H44 in terms of the dimension n. In terms of the dimension n. So what I did was wrong, because you have 1, 2, 3, and all. I was wrong. I was wrong. Let me compute once again. H33. No, sorry. H33 is 1, 2, 3, and all. And this, no, sorry, all and 1, 2, 3 is different. All and 1, 2, 3. Okay, so I'm computing in 3 steps. Here is all. Let's see if I made it correct. Yeah, I made it correct. I made it correct, I think. Is it a square matrix? Size. Yes, it's a square matrix. Size H44. Okay, so it's correct. Yeah, it has the same dimension. Okay, let's see if I was right. Rank H33. You see, it's 2. It's 2. Okay, and now let's compute the rank in 2 steps. H22 is all and 1 through 2, 1 through 2, and all. This is H22. Okay. Look. You see? You see, it's already got 2 columns of zeros. You see that? Okay. So rank. You see, it's once again 2. Okay, it's once again 2. So indeed, the minimal dimension, the dimension of the minimal realization is 2. Okay, the dimension of the minimal realization is 2. Now let's just check and see how a min-real works, and have a comment about this command, minimal realization. Yeah, that's where min-real comes from. Okay, so min-real of cis produces for a given LTA model cis an equivalent model M-cis, where all canceling pole zero pairs. Okay, this is difficult because we don't know what the zero of a multiple input, multiple output system is. Of a single input, single output system is very easy, but of a MIMO system, this is difficult. Okay, min-real produces a minimal realization or whatever. Oh, you can also return so you can also compute the structural decomposition transformation. You know, the T matrix that builds you all those funny little looking blocks from which you pick the minimal part. Okay, so if we go back to the code, let's go back to the code. Again, I understand you can see my screen. Okay, you do that, huh?
Yeah.
Okay, fine.
Yes, it's visible.
Okay, great. So I'm trying to make this window, okay, just like that. Okay. So where was I? Oh yeah, no, actually I computed it. I used this command. So let's look at U. Let's look at U. This is U. Okay, this is the coordinate transformation for the system. And now let's compute U, A, U. It's an orthogonal transformation. So you, instead of inverse, we use transposed, which is very nice numerically. Okay. U times cis A. This is how you call the A matrix from an object called state space system. It's cis dot A. So this is the A matrix. We compute that, and you see, look at the blocks. Look at the blocks. Okay, and then go to min real. Go to min cis. Okay. Let's see where it is. You see, minimal AM. This is the minimal realization he has computed. Now we have to see where we find this block here. Look, this is the A22 final block. You see here? Down here in the down right corner. Look, this is the A minimal here. Okay, emphasized very nicely by the coordinate transformation U. Okay, it's very interesting, isn't it? So that's how you compute. Again, I'm telling you once again, this is a minimal realization, so it's exact. Okay, it's canceling all the uncontrollable and the unobservable parts of the system. It's only keeping the controllable and the observable part. This is no approximation. Again, this is no approximation. In your assignment for next week, you'll look at functions which can be considered approximations of the system, because you have the CD player, which is a 120 by 120 system, and you can approximate, of course, at the extreme, in an exaggerated way and in a degenerate way, you can approximate the CD player with a constant transfer function. How can you do that? Only if you keep the steady state response. Okay, but that's an approximation. This is not an approximation. This is totally exact. How do I prove that? Easy. Let's compute the step function. Okay, the step function of cis and min cis. I'm not sure if this is working. Apparently it is. It's busy. Just hold on a second. There you go. You see? The responses are identical. You cannot tell between black and blue. You cannot say anything. You see? The responses are identical. Look, black and blue. They're totally, because they are one and the same system. It's identical. This is not an approximation. However, if you compute if you compute you use an approximation, okay? Let's see the difference. Let's see the difference. I'm going to introduce a MATLAB command called baltrunc. It comes from the method we are going to talk about soon, called balance truncation. It's a method to approximate a dynamical system. Okay? Help baltrunc. I think it's correct. No, it's not correct. Help balreal. This is okay. Modred. This is the command. Modred. Okay. This is an approximation command. Something we are going to learn about quite soon. Okay. Simplifies the state space model SIS by discarding states that have to be eliminated. Okay. Eliminated. So, okay, the method we use is truncate. Okay, truncate. All right. So let's go back to our example here. Okay. I don't know what this diaxis is actually. Let's see what we are trying to find out. Diaxis. What is this guy? Diaxis. Oh, okay, this is a diagonal version of the system. Okay, so I wanted a diagonal form of the minimal realization. I wanted a diagonal form of the an equivalent, because you know there is an infinity of minimal realization. I chose the one that you see emphasizes the eigenvalues of the system in an ascending order. Okay, so this is just an equivalence transformation I applied with this diaxis command, this canon command. Yeah. Okay, so now I'm trying to use approximation. I'm calling it like this, is modred. Okay, modred of min cis, because it has to be minimal, of min cis, and I'm going to use truncate. We are going to explain all of this when we talk about balance truncation, so no need to worry. There's something wrong. Oh, because I wanted something to eliminate. Yeah, I need something else. Let's see. Let's not use this. Let's just use anything for the time being. I just want to use modred. Oh, it's not working. Why? More than input arguments. Modred. Cannot use just modred. Oh, I need to eliminate something. Okay. Well, what am I going to eliminate? It's ball red as well. Let's use ball red instead of mod red, because I want to use something simple, because I just need to use something. Ball red. Ball red 1. Okay. So this is the approximation from order 2 to order 1 of my system. You see? Look, 2 to 1. Okay, so now let's do step of sys, the original system, the minimal realization, min sys, and the approx, and see that there is a difference. Okay. We check the difference between them. Now where's the picture? Here is the picture. You see, there is difference. Why can I not see the difference so well? There is a difference between them. It's difficult to realize, but there is a difference between all of these guys. Look at least look at this output here. You see? Look at the yellow, which is the original, and look at the yellow, sorry, which is not the original, which is the approximation, and look at the red, which is the minimal realization. Okay, which is the minimal realization. Okay, so there is a difference. There is a difference. Okay, let's just now plot the approx, or the min sys and approx. Maybe we get a clearer picture. Let's make min sys with x's, and let's make approx with stars. Okay, because you can tell MATLAB. Okay, it's gonna look bad. Okay, but you see, here you see difference. Here don't see much difference, but there is difference between the x and the stars. Okay, so I just plotted now. Three guys. Okay, but this last one is an approximation. It's a very good approximation because the system is very small. It's because the minimal realization is 2, and you go from approximation from 2 to 1. So essentially, it's a very good approximation. Okay, a very good approximation, and it's completely different from the minimal realization we have just computed. This is what I wanted to emphasize. Okay, so there's three discussion. There's two different discussion. The discussion of a minimal realization, essentially, you extract the controllable and the observable part, which is the relevant part of the dynamics from an input-output perspective. So the rest is just clutter. It's useless. Okay, the rest can be thrown away. Whereas in approximation, you force throwing away dynamics which you consider not relevant for your system. This is the difference between modeling, between the minimal realization problem and the approximation problem. Do you kind of understand? Is it a little bit clear, the difference between the minimal realization and approximation? I'm asking you.
Yes, I guess it is.
I guess it is. You'll see it later much clearer when we discuss explicitly, specifically these techniques. Okay. What we had here before, let's run this guy once again, because I want to see. So I had here also the transfer function. So you can, if you have a look, from the complicated matrices that I get, the transfer matrix, this is from channel 1 to 1, from input 1 to output 1 to output 2, input 2 to output 1, output 2. You realize that it's 0, so this is a diagonal transfer matrix. This is why it is so easy, the example. That's why the example is so easy, okay? Because it is a diagonal transfer matrix, okay? This is how I got it. Okay? I think I'm going to save this guy to your folder, because this is something I used to do for the automatic control systems course, because they also study a part of these things. Okay, so let me move it now to your class, teaching DCR ACS simulations. Okay, this is important. Let's save it here. So you later on, you'll have an assignment after this one. For the next week, you'll get an assignment to play with these things. Okay, to play with these things. But you can do it yourself, and you can see, as you can see, you've got a lot of commands. Mineral, S mineral. Let's see, there is an S something, because probably there are more efficient commands in MATLAB implemented. Simplifies the model, eliminating all model components that are not connected to any input or output. This is very also interesting. Okay, so it says here it also eliminates the structurally disconnected states. So even if they are not important, so if they might be controllable and not observable, observable and not controllable. This is my understanding of these things. And this guy clearly determines these parts and throws them away. Okay, and throws them away. Okay. All right. All right. I saw here some other things. Okay. Let me go back to the folder where I extracted this problem from the examples used for the people who study these things. Let's see what these guys do. Okay. Yeah, here I was just showing some transfer matrices. Okay, I was showing transfer matrices. I was solving the realization problem, just like we discussed. Okay, so okay, I was building here. I was solving here the realization problem. So I had the coefficients K1, K0, K1, and K2. I was building. I also had the gammas, which are present here. 1, 2, and -2. So these are actually the minus gammas from the standard canonical forms we discussed. Okay, and now I'm building the state space realization. Okay, and I'm checking the observability and the controllability. Okay, and I'm getting again a minimal realization as well as the canonical minimal realization. Okay, and in this part, I think I'm doing the same, but with a different example for order 2. So let's just check it here. You realize here that the dimensions of A, B, C are quite large. So it's very important to compute the minimal realizations. Let's run the simulation. Okay, let's see the results. Okay, so look here. Okay, look at the method. So this is the main system. It's 9 by 9. Okay, it has 3 inputs and 1 output. 3 inputs and 1 output. The matrix R is huge, but the system is controllable apparently. Why is it controllable? Because if you notice here, I wrote a controller canonical form. This here is a controller canonical form. This is a controller canonical form. Okay. Let me save them to our class. Okay. Save them to our class. Okay, so they are saved now, so we can change stuff. So this is controller canonical form. Controller canonical form. Let's make it a comment. So this is the controller canonical controller canonical form. Okay. All right. This is the state space system. State space realization. Okay. This is checking controllability and observability. Okay. Minimal realization. Okay. All right, let's save it. Cool. So look, Q has dimension 3. So that means that probably the dimension of the minimal realization is 3. Dimension of the minimal realization is 3. Okay, so let's check again. H99 is Q times R. Okay, it's a huge matrix. So rank H99 is 3. So indeed, 3 is the dimension of the minimal realization. That's 3. You see? So this is quite huge, you see? It's a lot of equations which are absolutely irrelevant. So 6 states can be removed once you apply a minimal realization command like this one. And then you get the minimal realization, dimension 3, 3 states, 3 inputs, 1 output. Okay? And this is the coordinate transformation that makes it so. This is the coordinate transformation that makes it so. And now we can make, you see, this is the normal minimal realization, the classic minimal realization built merely applying the algorithm we discussed. But I can write a simple equivalent minimal realization with a diagonal form, which is very useful and very simple to use. Very simple to use. Okay. And this is the transfer matrix. Okay. This is the transfer matrix. This is very interesting, huh? So from 9 we go down to 3. We go down to 3. Okay. Okay. And again, we do approx. Let's approximate this with the simplest possible. So we do approx is ball red using balanced truncation, which we're going to discuss. And this is the very simple scalar model of everything. Okay. And now let's try again step of min sys the prox. Let's hope we get something quite visible. No? Not necessarily. I'm not sure why I don't see. Okay, this is the approximate system. Okay. And I want to do the step of min sys. Something different. Why I'm not seeing different, I don't understand. So they are computed very well, these approximations. You know. Okay. The system is not stable, by the way. Let's look at the diagonal realization, because I suppose it's not. No, it's not stable because it has s-1 in it. Yeah, sure. It's not, because there is a -1 eigenvalue. So it's not stable. Okay. This is how things work with these things. Have you got any questions about minimal realizations that you'd like me to answer?
I have a
Please,
question.
Go ahead.
So as I see, the minimal realization is very good even it's equivalent with the system, an application system.
Can you say again? So even what? Even if what?
Is equivalent with the system.
Yeah, the minimal realization is equivalent. It's identical. I told you, it's completely exact. Yeah, that's true.
So why would we need something else if minimal?
Because these are simple examples. These are simple examples. Minimal realizations usually can be very large. Okay. For instance, the CD player. Let's go to the CD player. Do you want to do that? Let's look at the CD player. No, it's not working. Why? Oh, no, I think it's CD underscore player. Sorry about that. No,
Because you are not where the CD player is.
Why not? Because I should be. Yeah, I should be. Oh no, it's CD player. It's I had the command wrong. Okay. What the hell?
The current folder is in MATLAB C.
Oh, is in MATLAB. Okay,
So,
never mind. Let me do it like this. Okay, so he loaded the MATLAB. Okay, look at the matrices of the CD player. A is 120. You see?
Sparse.
Never mind, but it's 120. Sparse or not sparse, it's 120. Okay. So now what I'm going to do is CD. I'm going to make the state space is SS of A, B, C, and zeros 2 by 2. Okay, so this is your system. Okay, can you see that? Huge system. Yeah, 120. Okay, now let's check the minimal dimension. You want to do that?
Yeah.
Okay. Help CTRBF. No, this is not good. I expected something else. Never mind. Rank of CTRB of the CD player. What's wrong? SVD. CD 2x2 system. Okay. 1 second, please. Here it is. Okay. He cannot even compute this guy. You see? He cannot even compute it. This guy. Because it's of large dimension. But I'm telling you, it's minimal. Okay. I'm telling you, it's minimal. Okay. Let's do it like this. Mineral of CD. Let's see if it does something. Okay. Now let's see size answer dot A. You see, it's huge. It's huge, and it's not even correct. You see? Because it should be 120. So the minimal realization of this guy is 120. Understand? So it's not 2 or 3. So it's difficult to use. Okay? Hello, you still there?
I have the microphone off.
Sure. So you see, it's 118. It's even incorrect. So he cannot even compute it properly at this dimension because the CD player is already in a minimal form. You see? It's already minimal. So in general, we do approximation because the minimal realizations of the phenomena we study have huge dimensions. Think of the discretized version of a heat equation. Okay, I have that example somewhere. The discretized version of a heat equation. I'm going to give it to you to play with. Okay? A heat equation is a partial differential equation. You know the heat equation. Have you heard about it before?
Yeah, but I don't know
Okay,
right now.
I'm just telling you, it's a partial differential equation. A partial differential equation cannot be solved in this life. Okay? The problem is that to solve a partial differential equation, you need to discretize the space. So what's a partial differential equation? Is a dynamic, it gives dynamics which depends on both space and time. Okay? We agree. Fine. Since it's got this double dependence, we cannot solve it. Hence, how do we usually solve this? We transform the partial differential equation into an ordinary differential equation. It's already an approximation because we discretize the space, and in this grid, in the resulting grid of the discretized space, we write in each point differential equations, ordinary differential equations, those that we see in this class. Hence, the heat equation can be approximated by a huge number of differential equations, hundreds, thousands, tens of thousands, millions, if you like, of equations. And those are already minimal. So the mean sys is not reducing the dimension. That's why we do this course, and does not reduce complexity. Okay? So the examples we discussed in this class, the previous examples I showed you, they're only simple theoretical examples. But look at the CD player. Okay? You understand?
Yeah, now I understand. Thank you.
Okay, so in general, minimal realizations are huge and they need to be approximated. The examples we discussed, they're just simple examples. Okay? They're just simple examples. Okay, fine. So if this is clear, I'm going to discuss the final subject of this class, Lyapunov and Sylvester equations. For this reason, we can compute using Liap. So we have, for Sylvester, we have the Sylv or the Sylvester. Now the new command in MATLAB is Sylvester. The Sylvester solves the Sylvester equation ax plus xb is c. This is a Sylvester equation. And Liap is the command for Lyapunov equations, but nowadays is also useful for Sylvester equations. So Liap is also solving both Sylvester and Lyapunov equations. Please keep in mind that the algorithms to solve Sylvester and Lyapunov equations are a different subject. Okay, so there's hundreds of methods to efficiently try to solve these equations, because when the dimensions of the matrices increase, okay, usually these equations are difficult to solve. And this is the case with Lyapunov equations. And due to these problems, techniques such as balance truncation suffer from this issue, because Lyapunov equations are difficult to solve. And even if we have numerical techniques, they are not good enough. Okay, so for instance, for the Lyapunov equations, you also have this function Liap call. Liap call solves the Lyapunov equation based on the Koleski factorization. I hope you remember from numerical methods what a Koleski factorization is. If you don't remember, okay, so this is a triangular factorization with triangular factors, okay, which can help to solve this equation in an easier fashion. Okay. For instance, let's go to this example. Okay. So let's solve, for instance, the controllability Gramian. The controllability Gramian. Let's call it W. The controllability Gramian is the solution of the Lyapunov equation, Liap of A okay, and B transpose, okay. Also, minimal realizations can also be determined from the Gramians for stable systems. The Gramians can also tell us, based on their ranks and on their positive definiteness or semi-positive definiteness, if they are minimal or not. Because if the semi-positive Gramian contains zero eigenvalues, the zero eigenvalues of the Gramian mean uncontrollable states. Okay, so let's do this. Sorry, B transpose. I made transpose is this. Look, it's full of zeros. It's full of zeros. Okay. Rank W. 100. So he computed it for the CD player. This is for the CD player. Because of the large dimension, his computation is wrong. At first he said 118, and now he says 116. So this is a bit wrong. This is a bit wrong. Let's see the eigenvalues of W and see where the problem is. Please also keep in mind that it's stable. The system is stable. So you should have, okay, so it's very small values. You should also have, you see, you have some huge eigenvalues and also very small eigenvalues, and probably many of them are zero. Okay, let's see what Liap call does. Okay, so this looks a bit better. Let's see if Liap call gave us a better result. Rank W. Oh, look, Liap call is wonderful. Look, this is an accurate result. So indeed, the system is controllable because the controllability Gramian, please recall from the previous chapter, is positive definite. Oh, this is great. So Liap call is more efficient than Liap. Liap call is more efficient than Liap. Okay, eigenvalue still didn't do much. It's still quite useless because there are these huge numbers that you have here. These are huge numbers, okay? These are huge numbers, okay? Look, huge numbers. So this is wonderful. So the controllability Gramian has rank 120. Wonderful. Let's compute the observability Gramian. Let's call it M. Remember from the previous chapter, Gramians. Please study them carefully. Liap call, I love this command because it gives me more accurate results of A transpose and C transpose times C. This is the Lyapunov equation we need to solve. This is M, and let's see rank M. Oh, it's 120. So the system is also observable. Now, Collie, where is my friend? Mate, the guy who talked to me a few minutes ago. Can you come back to the microphone, please?
Yeah, I'm here.
So now you see the confirmation.
Mm-hmm.
The CD player has the minimal dimension 120. The Gramians told me that because the Gramians could be more efficiently computed. But you see, even with dimension 120, we still have computational issues. That's why we need approximation, you see? That's why I gave you this toy example, CD player and the building. That's why I gave them to you to play with. Okay? All right? So Liap call, computation of Lyapunov equations based on the Koleski factors is much better than Liap. Okay? All right? Okay, mates. All right. So that's enough for me today. If you have any more questions, please. Yeah, that's me in Naples many years ago. Actually, 8 years ago. So if you have any more questions, please. Questions, please? I'm going to stop the recording at this